For decades, black holes have been some of the most enigmatic objects in the cosmos, sparking the curiosity of scientists and the general public alike. Recently, theoretical physicist Michio Kaku has shaken the scientific community with an astonishing revelation. We may have finally discovered what lies inside a black hole. This is not just another breakthrough in astrophysics. It completely redefines our understanding of space, time, and the fundamental nature of reality itself. But before we begin, like and subscribe for more updates. The breakthrough revolves around a new model of the interior of black holes, based on the synthesis of quantum mechanics and general relativity. Traditionally, black holes have been described by Einstein's theory of general relativity, which presents them as regions of spacetime with such intense gravitational acceleration that nothing, not even light, can escape their pull. According to this classical model, any matter that falls into a black hole is irrevocably pulled toward its central singularity, a point of infinite density where the known laws of physics cease to apply. For years, this singularity has been unsolved, a dark region beyond empirical verification. However, Kaku's announcement indicates that this mystery may begin to be solved. At the center of this development is a revolutionary hypothesis. Based on string theory and quantum information, he and his team have been working with quantum gravity models that seek to unify the scale structure of general relativity with the probabilistic nature of quantum mechanics. Using advanced simulations and new data from gravitational wave detectors and the Event Horizon Telescope, the team has proposed a theoretical structure within black holes that is much more complex than a simple singularity. Instead of a point of infinite density, the center of a black hole could harbor what is called a fuzzball, a concept proposed within string theory. This idea replaces the singularity with a dense, tangled network of strings, which, according to string theory, are the fundamental building blocks of the universe. These strings vibrate at different frequencies, giving rise to all the particles and forces we observe. If Kaku's team is correct, the interior of a black hole would be a compressed sphere of quantum information held together by gravity but not collapsing into a singularity. This would mean that instead of being a dead end for physics, a black hole could be a bridge to understanding the quantum nature of the cosmos. The implications are enormous. For one thing, this theory addresses the famous black hole information paradox, a problem that arises from the contradiction between quantum mechanics and general relativity. According to quantum theory, information about a physical system can never be lost. But when matter falls into a black hole, classical theories suggest that the information it carries is destroyed forever. This contradiction has puzzled us for decades. The new theory, however, proposes that information is not lost, but rather encoded in the event horizon or within the fuzzball itself. This would maintain consistency with quantum mechanics and bring us one step closer to a unified theory of everything. One of the most fascinating consequences of this theory is the possible redefinition of what a black hole actually is. It would no longer be simply a cosmic vacuum cleaner, a monster devouring everything in its path. It could now be seen as a sophisticated information processor and even as a storage device containing the history of everything it has consumed. If we could access that information, we could theoretically reconstruct the past of entire star systems or even civilizations that were swallowed up by these titanic structures. Although we are far from being able to do this in practice, the mere idea already transforms our view of black holes, not as destroyers, but as archivists of cosmic history. This interpretation also opens up new possibilities for exploring the multiverse theory. If black holes contain compressed dimensions or regions governed by quantum laws, then each black hole could be a gateway to another universe or a different sector of the multiverse. Kaku's findings have reignited discussions about wormholes and Einstein-Rosen bridges, concepts that once seemed like science fiction. If the interior is no longer an unknowable singularity, it becomes possible, at least in theory, to consider passing through a black hole, not as a suicidal leap into oblivion, but as a journey through a quantum tunnel to another reality. The technology used to reach these conclusions also represents a quantum leap in itself. Advances in gravitational wave astronomy have allowed scientists to hear the ripples caused by cosmic collisions involving black holes. These signals carry information about the mass, spin, and even the possible internal structure of black holes. Meanwhile, the Event Horizon Telescope has delivered the first-ever images of a black hole's event horizon, providing a visual outline of these invisible giants. Kaku's team combined these data streams using sophisticated algorithms and quantum models to simulate what might be happening beyond the event horizon. These simulations revealed unusual patterns that cannot be explained by traditional singularity models. For example, certain gravitational echoes, faint reverberations following black hole mergers, suggest that space and time behave in exotic ways near and within the event horizon. These echoes point to structures that match the predictions of string theory. Although the evidence is indirect, these pieces of evidence create a compelling argument in favor of the fuzzball model and the idea that black holes are not empty, but rather vibrating quantum objects. These revelations also have philosophical implications. The possibility that black holes can encode information and preserve the essence of what they consume brings new meaning to the concept of continuity in the universe. It challenges the notion of end and loss, suggesting instead that nothing truly disappears from the cosmic stage. Even in death, stars may continue to exist, not only in the remnants they leave behind, but in the quantum traces recorded within the black holes they fed. This idea is profoundly transformative. It reconstructs the image of black holes from cosmic executioners to guardians of the universe's memory. The idea that atoms from stars, energy from extinct planets, and even the echoes of intelligent beings could persist in some form within the interior of a black hole is not only poetic, but is supported by the most advanced physics. Kaku's revelation forces us to reconsider our relationship with the universe. We are not just passive observers looking out into space. We are participants in an information-rich cosmos, intricately connected through a web of quantum entanglement. The very nature of time may also need to be revised in light of these findings. Inside a black hole, time behaves radically differently from how we know it. According to some models, time could become spatial in character, suggesting a realm where past, present, and future coexist in a static state. If this is true, then what exists inside a black hole is not just the matter it has consumed, but every moment associated with that matter. This opens up the possibility that time travel, long considered science fiction, may find a theoretical basis within the physics of black holes. Michio Kaku's announcement also revitalizes the search for a theory of everything, a single unified framework that explains all physical phenomena. The compatibility between the fuzzball concept and string theory could serve as the bridge sought for more than a century to connect quantum mechanics and general relativity. This development makes the seemingly impossible task of reconciling the macro and micro realms of the universe seem not only plausible, but inevitable. The black hole, once seen as an obstacle in this quest, could actually be the key. Another intriguing consequence of the new model involves Hawking radiation, the process by which black holes evaporate over immense periods of time. Previously, this radiation was thought to carry little or no information, simply representing the slow death of a black hole. But if the internal structure encodes data, then Hawking radiation could be subtly influenced by the information contained within. This would mean that black holes do not simply disappear into nothingness. They could emit a whisper of their secrets before fading away. Extracting and decoding that whisper could offer humanity a new way to study objects that are far beyond our reach. Furthermore, this breakthrough challenges the existing boundaries between what is knowable and what is not. For much of scientific history, the event horizon has represented a frontier of ignorance, a point beyond which no information could return. But Kaku's model calls that limitation into question by viewing the event horizon not as a wall, but as a veil that can be deciphered. The black hole ceases to be an abyss and becomes a vault whose secrets are protected but not inaccessible. This conceptual shift could inspire new technologies aimed at deciphering the patterns embedded in the radiation or gravitational waves emitted by these exotic entities. The resonance of this discovery goes beyond science and into culture. Artists, philosophers, and writers will inevitably reflect on the symbolic implications of a cosmos where nothing is lost, where even the deepest voids are filled with information and structure. It transforms black holes from icons of nihilism to symbols of resilience and transformation. The idea that knowledge, matter, and even perhaps consciousness persist within these celestial engines touches on the deepest human need to be remembered, to be preserved, to be understood.